Hey guys, in this video, we're going to be talking about significant figures and dimensional analysis. So what are significant figures? Well, significant figures are the number of reliably known digits in a number or measurement. So let's take, for example, 2.25 centimeters. In this measurement, we have three significant figures, 2, 2, and 5. So we're going to write 3 sigfigs, or significant figures. What about 3.266 meters? This is 4 sigfigs. But what about 0.13 seconds? Well, leading zeros never count. Leading zeros are the zeros in front of a number. They only serve sort of an aesthetic purpose. So we only have 2 significant figures here, the 1 and the 3. And similarly, if we have 0.0022 meters, then we only have 2 significant figures because leading zeros don't count towards the number of significant figures. But what if we have 0.2000 hours? Well, zeros after the number do count towards the number of significant figures. So we have 4 significant figures here. So if we have 0.030010 meters, then we have 1, 2, 3, 4, 5 significant figures. That is, we have 3, 0, 0, 1, and 0 are all significant. What about 60 seconds? Well, if we say it is roughly 60 seconds, then there's only one significant figure since the 0 is merely a placeholder. The exact measurement could be 61, it could be 62. But if we don't have a suggestion that 60 is a rough approximation, then we can often assume that it is 60 seconds within an accuracy of about 1 or 2 seconds. And then the 60 has 2 significant figures. What if it is precisely 60 seconds to within, let's say, plus or minus 0.1 seconds? Then we just write 60.0 seconds, and that is, of course, within 3 significant figures. So 60 seconds, 1 or 2, 60.0 seconds, 3 significant figures. Now, what if we are multiplying 2 measurements or dividing 2 measurements together? How many sigfigs should the end result have? In general, we say that the final result of a multiplication or division should have no more digits than the numerical value with the fewest significant figures. So if we are multiplying 3.00 seconds times 4.000 seconds, the end result should have no more digits than the numerical value with the fewest sigfigs. So the value with the fewest sigfigs is 3.00 seconds. It has 3 sigfigs. The end result should have no more than 3 sigfigs. So the end result is 12.0 seconds squared. That is 3 sigfigs. Same for division. If we have 12 meters divided by 3.00 seconds. In the numerator, we have 2 sigfigs. In the denominator, we have 3. So the end result is going to have the fewer sigfigs, which is 2. So we have 4.0 meters per second. Now, it gets a little tricky when we have a constant. So what if we're just doing 12.0 meters over 3 seconds? At first glance, you would think that we have to have 4 meters per second because there's only 1 sigfig in the denominator. And you would be right in most cases. But we have to consider that 3 could be represented as 3.000 on and on. And in that way, it might have infinite sig figs. You have to remember that exact numbers do have infinite sig figs. So numbers derived from, say, definitions or exact counts. For example, 1 meter equals 100 centimeters. That has infinite sig figs. And when you're performing calculations involving such numbers, then they don't affect the number of sig figs in the result. But if a value like 3 seconds is a rounded version of a measurement or a calculation, that means it's a lower level of precision. So if 3 seconds represents like any value between 2.5 and 3.5 seconds, then yeah, it has one significant figure, and we should take the division assuming that the denominator has one sig fig. Now, when there is some ambiguity here, you want to use scientific notation. So we can replace 60 seconds, for example, with 6 times 10 to the 1 seconds. And that would clear up any ambiguity because it is clear here that we have one significant figure. Also, when adding or subtracting numbers, the final result should contain no more decimal places than the number with the fewest decimal places, not sig figs. So if we have 0.57 minus 3.6, the number here with the fewest decimal places is 3.6. It only has one digit after the decimal place. So this here is going to be 3.0. It's rounded to one decimal place. If we have 36 plus 8.2, well, the number with the fewest decimal places here is 36 because there is no decimal point. So we have 44 because it's rounded to the nearest ones place. And if we have 41.33 minus 6.33, we have 35.00. So we're not rounding to the number with the least sig figs, we're rounding to the number with the least decimal places, which is 2 in this case, so the end result has 2 decimal places as well. All right, let's move on to dimensional analysis. When we speak of the dimensions of a quantity, we're referring to the type of base units or base quantities that make it up. So the dimensions of area is always length squared, right? If you think about the area of a square, it's going to be the length squared. If you think about the area of a circle, it's going to be pi times the radius squared, and radius is measured with length. So that is also going to be the dimension L squared or length squared. And we write that in square brackets. So velocity, on the other hand, can be represented in units such as meters per second, miles per hour, kilometers per hour, and so on. But the dimensions are always a length, L, divided by a time, T. So we write that in square brackets as such, and this is velocity. And we call these dimensions. So why are dimensions useful? Well, we can actually use dimensions to work out relationships in formulas. And this is called dimensional analysis. One way we use dimensional analysis is to check if a relationship is incorrect. We know that if we multiply 2 dimensions on one side, then on the other side, we should have the same dimensions. Now, let's use the example v equals v0 plus 1/2 at squared. Okay, this stands for velocity. Velocity is equal to initial velocity plus 1/2 times acceleration times time squared. All numbers such as 1/2 or 3 or 0.6 are dimensionless quantities. Now, remember that we said velocity has the dimension length over time. And we represent it like this. And that is also the same for initial velocity. That's just the velocity at the initial point in time. And then we are adding 1/2, which doesn't even have a dimension, times acceleration. Now, we measure acceleration in the units meters per second squared in physics. So that means acceleration has dimension L over t squared, length over time squared, multiplied by time squared. Okay, and clearly this relationship checks out. We have that the dimension length over time is equal to the dimension length over time plus 0. And that cancels out, and we have a correct relationship. But just because the dimensions add up on both sides, that doesn't mean the relationship is necessarily true. We could add 2v equals v0 plus 1/2 at squared, and that would be incorrect, even though the dimensions still line up. It's just a tool in their toolbox to see if we have correct relationships. Okay, so let's say we have a simple pendulum of length L. Suppose that we can't really remember if the equation for period t, which is just the time to make one back and forth swing, is 2 pi times the square root of L over G, or is it t equals 2 pi times the square root of G over L? Let's use dimensional analysis here to quickly check which equation might be true. So t is measured in time. It's measured in seconds. And then 2 pi is dimensionless. And then we have the square root of length over gravity, over the gravitational constant g. And g is acceleration. G is an acceleration, so we have length over seconds squared, or time squared. And if we simplify, we have the square root of length times time squared over length. So length cancels out, and then we have the square root of time squared, which is just time. So we know that the first relationship is probably correct without having to check the second relationship. And we would go forward with our problem, assuming that the first one is correct. And that's it for the video, guys. Thanks for watching.